coming. Welcome our speaker Marcelo Garlet Milani from the NII in Tokyo, and he's going to speak about elementary bonds for the directed grid theorem, which will, it's topic-wise the same as the talk by Yelena Mutzi, but he's going to give us a different perspective on it.
Okay, thank you for the introduction and taking everyone for coming to talk. So we're talking about what's one of the main results of my PhD thesis, and that's the elementary bound with the directed grid theorem, and also talking about one of the main objects I've introduced in order to obtain this bound. And this tried to work with Michael Hatzel, Stefan Kreutzer, and Elena Musi. So before I tell you about the concrete results, I just want to give you like a little bit of the context in which this happens. And this is the concept of the parameter of directed tree width. So we're talking about directed graphs. And I'm not going to give you like the formal definition, but like the rough idea of directed tree width. It kind of captures how complex the strong-connected components of the digraph are, or also in a sense it captures the distance to being a cyclic. So if the digraphs are cyclic, the tree is going to be 0, and the more complicated the strong-connected components are, the larger this parameter is going to be. And when you have this kind of parameter, you can ask some questions, and for direct tree width, if we have like small tree width, then we can solve some problems using dynamic programming, for example, the disjoint path problem. But what we're going to talk today is not going to be about having small direct tree width, but it's more about what happens when the direct tree width is large. So when this parameter was introduced, there was this conjecture which states that if there is some sort of function f, such that if my digraph has sufficient large directed tree width.
This is very, very hard to.
Yes, it's almost
invisible.
invisible.
You can change the
Oh,
color
that is
now.
really awful.
Yeah, the light blue is not so good.
Okay, then I can try rewriting things. So green is readable, is it?
Well,
Not amazing, but better.
Maybe something reddish.
I don't like reddish.
Reddish is not good. Oh yeah.
So is this
Yeah,
okay, right?
that
So,
works.
okay, so there's some function n, and so every digraph d which has reasonably large tree width, so the direct tree width of d is at least this function, then contains the cylindrical grid. Order k as a butterfly minor. So the cylindrical grid is this digraph. We have several concentric cycles. So k many cycles, and they all go in the same direction. And we also have k pairs of paths going like outwards and then inwards. So kind of like expect like many cycles, since you're kind of measuring how complicated the strong components are. And so they conject that you always find this as a butterfly minor, and butterfly minor is a similar relation to minors for analytic graphs. So you're allowed to delete vertices, delete edges, and you can contract edges which are either the unique outgoing edge of a vertex or the unique incoming edge of the vertex. So this was conjectured in 2001, and then a couple of years later, Kawarabayashi and Kreutzer, they gave non-elementary upper bound for this function f. And so non-elementary, I'm not going to give you like the exact definition of what elementary means, but if you have a function which grows faster than some power tower, so f of k, if it's like larger than this, and the number of like 2s that you would stack on your power tower, if that's again some function of k, then this is not elementary. And for the other hand, you have a function where the number of levels that you get in power tower, if that's constant, then that's going to be an elementary function. So for our setting, this is like what's relevant, like it's the height of the power tower. And so before I tell you like how we obtained this, I would just like to talk a little bit about how this non-elementary functions even pop up in this kind of result. So with this, I'm going to focus on what two papers do. Is yellow readable?
Mm-hmm.
Okay, so first on the paper about the directly grid theorem, and also on the paper about backing direct secrets. So they have some arguments in common. And one thing that often causes this non-elementary functions in their arguments is to have some sort of like recursive argument. Like you apply induction, and you're always like playing some function. And in both papers, they have an object that they need to find, which ends up causing this functions, and that's the acyclic grid. So they both need at some point to get some acyclic grid. So that's a grid where the paths are oriented from top to bottom and from left to right. And one way where you can kind of like argue about getting this grid like on a very high level fashion is that you get like many paths, and you want to like iteratively construct your column. So you're gonna try to argue I have like some other linkage, and I'm gonna have some path that intersects a few of my blue paths in an ordered fashion. And for the other paths, either I not do in the correct order or I don't intersect at all. So that means I kind of have to like drop these paths, and then I kind of recurse on the rest. I kind of lose something, and I try to recurse on the rest of this diagram. So what I get is that like my function f at the beginning, if I want to have k columns, I'm gonna need to have like f of k many paths. So to do my recursion, I'm gonna need f of k minus 1. And so if my recursion relation is something like f of k is some g of f of k minus 1, well, if this function g is single exponential, then this argument is gonna make the height of tower to depend like on the number of iterations that I make. So that's how they often end up getting this non-elementary bounds, because they apply for this step something like Ramsey or something like this once, and since you do this recursively, this is gonna blow up the power tower. So when trying to go for a non-elementary bounds, the main challenge now is that we kind of cannot use pseudo-polynomial functions whenever we try to do induction or something like this. So you we're kind of restricted to using like Ramsey or Bezier-Hole principle only a constant number of times. Okay, so what are results in this setting? So the first thing that we get is that we have a function f1 of k, which is now a power tower of height 8, such that every digraph D, which has a sufficient high directed tree width, contains the acyclic grid. As a butterfly minor. And we also get the property that the end of the grid is going to be falling to the beginning. So if I look at my grid, if I consider this set, let's call it A, and this set, let's call it B, then A is going to be well linked to B. And by well linked, I mean if I take any subset A prime here and subset A B prime, if they have the same size, then I'm going to find disjoint paths connecting those two. So that's the first result, and by having this, we can already apply some existing results to conclude the following. So this is what's known as Younger's conjecture. So Reed, Robertson, Seymour, and Thomas, they gave non-elementary upper bound for this statement. And we can already, applying some results they have, we can already obtain an elementary bound for this. So we get some function f2 of k, get some power tower, and here the height stays the same, so the set that we need from them is actually polynomial, such that we get the following property. So every digraph D satisfies one of the two following properties. So either we get k disjoint cycles, so we get like many disjoint cycles, or we're gonna have in a digraph D some set X, so set of vertices, such that whenever when we delete the set X, so everything, the rest becomes a cyclic. So every cycle I have is hit by X. And of course, what we want now is that the set X is small, and the size is going to be the function that we get. So we define many disjoint cycles, or we can hit all disjoint cycles using a somewhat small set. And the third result that you obtain, that's the grid theorem. And so what we get now here is that we obtain a function f3 of k, which is a power tower, and the height gets a little bit larger. It's going to be 22. So we get every digraph D with large tree width. Contains a cylindrical grid of order k as a butterfly map. Okay, so before I tell you how we did this in our proof, I would like to briefly talk about what happens in the undirected setting. So there is also a grid theorem for undirected graphs that came before the one for directed graphs. And that's one of the results of the graph finder series by Carlson and Seymour. And so what they showed is that there is some function f, such that now every graph with undirected tree width sufficiently large contains the KK grid plus or minus. So originally the function to obtain is like very large, but this was improved a few years ago by Chekuri and Chuzhoy to a polynomial function. And one thing that they introduce in order to obtain this polynomial function is the concept of a path of set system. And roughly speaking, the idea of the path of set system is that you kind of separate the connectivity that you get from the grid from its topology. So you first try to find an object which kind of has the same connectivity properties that the grid has, and then after you have this, then you try to make what you get planar in order to obtain the grid. So that's kind of roughly the idea of this path of set system. In our proof, what we're going to do is that we're going to try to get a similar object, but for digraphs, that somehow captures the connectivity of the grid, and then in the end we try to get this object to be planar. So let's first take a look at what kind of grids we have in the directed setting. So as you can imagine, there are many ways of orienting a grid. So one thing we already talk about, that's the cyclic grid. We can orient paths from top to bottom and from left to right. And another way of orienting this is we can go from left to right and then have the columns to be alternating. So one then goes down, the other goes up, and so on. And the third way of orienting this grid is what we saw before with the cylindrical grid. So we can have like many cycles with these alternating columns going in and out. So the one tomato is called a fence, and this is the cylindrical grid. So let's take a bit of a look on what kind of connectivity we get from these grids. And the easiest case to understand is the fence. So if I have a sufficiently large fence and I take like a few vertices on the left side and a few vertices on the right side, then it's not so hard to see that it doesn't matter how I pick the vertices, since I have paths going both directions, up and down, I can always connect the left side with the right side. So here I can kind of like go down here, go to the right, here I can just go straight, here I can also go down to the right. Like if I have enough columns, I can kind of always move one path to the row that I want to use, and then use that row to reach the end. So what you get from the fence is that the left side, let's say it's A and the right side is B, you get that A is all linked to B. So it doesn't matter where I start or where I end, I can always do this connection. For the cylindrical grid, if your dot is slightly different, you can actually see that it kind of contains a fence plus this linkage quite at the end back to the beginning. So we're going to again get this row linkedness, but since we're like in a cycle, we can kind of get row linkedness also in both directions. And for the cylindrical grid, it kind of gets like a bit trickier, because if I want to go from like the bottom here to the top, well, I can't because I can only go downwards. But if I have something that's like mixed, where I sometimes want to go down, but sometimes I want to go up, then suddenly that's possible. So we have at first like some issue of properly describing what's the connectivity given us by the cylindrical grid. So the first thing that we're going to do is we're going to try to properly describe this and say what is this. So towards this end, we defined this linkedness property. So that's what we call ordered linkedness. And it works as follows. So we have these two sets A and B. So that's the two sets of vertices. And additionally, we have two linear orderings. So the set A has a linear ordering, and the set B also has some linear ordering. So for this picture, I'm going to just draw both sets like going from top to bottom, this ordering. So you can also think that this is just like numbered, like 1, 2, 3. And to make things easier, I'm going to assume that A and B have the same size. So that's already enough for our results. And so we have like these two sets with the orderings, and we're going to say that A with this ordering is order linked to B. If the following happens, so again we can take a subset A prime and B prime of A and B, so we can take vertices here. But you have two conditions, and the first of them is such they have to have the same size. But as a same for the cylindrical grid, we cannot just pick any two sets that we want. We need to choose them in a careful way. And so how do we describe this careful way is that when I pick my set B prime, I can now define uniquely a bijection from A prime to B prime by mapping the first element of A prime to the first of B prime, the second to second, and so on. As it is going to be my bijection we're going to call pi. And since I have orderings on both sides, this is unique. And what we're going to require from B prime is that B prime is never above A prime. So now I'm going to give you a formal definition because that gets a little bit long, but what we actually want here, if you think about like this numbering that you have on both sets, what I want is that when I take this, my bijection pi, that the number on the left is always at most the number that I get on the right. So in a sense, when I'm going from A prime to B prime, I'm not going up, I'm always going downwards with respect to this ordering. And so whenever we pick sets that look like this, order linkedness is going to tell us the following, that not only we have a linkage connecting A prime to B prime, but additionally you have that every A in A prime goes to pi of A in B prime. So in a sense, like this condition of the sets makes this one way like weaker than row linkedness because we cannot pick any set that we want. But at the same time, this makes us a little bit stronger because we also can guarantee how this link is going to look like. So we're not getting any permutation, but we're linking exactly this vertex to this vertex, this vertex to this vertex, and so on. Okay, so what we can do now is that when we go back to the acyclic grid, we can see that if I take the left side and the right side, that A is order linked to B. So this is roughly like the types of connectivity that we get from the grids. And so now we can try to define this path of set system equivalent object that somehow captures this connectivity properties. And the way that we do it is the following. So we have several clusters. So these are going to be disjoint subgraphs in my digraph. They're going to have two sides, the A side and the B side. One, A2, B2, and so on. And we're going to have like some linkage connecting the B set of one cluster to the A set of the other. So this is just going to connect them somehow. And now if you want to capture what the fence is doing, what I'm going to require is that my AI is well linked to BI. And then this is going to be what we call a path of well linked sets. And if you're on the acyclic grid, what you're going to require is that AI is order linked to BI, which is going to give us the path of order linked sets. And from cylindrical grid, what we require is that if we take the last cluster here and look at the first cluster, then we're going to have a linkage connecting both of them, which is disjoint from the rest, so we cannot hit any cluster. So this, when you have this linkage connecting the cluster like this, and the sets inside are well linked, then we get what we call the cycle of well linked sets. So these are the three objects that we obtain with the goal of kind of like capturing the connectivity given by these three types of grids. And in the end, we can show that we kind of get some like functional equivalence between these two things. So the cycle of linked sets is going to contain the cylindrical grid. The path of linked sets is going to contain the fence. And the path of order linked sets is going to contain the cyclic grid. But saying this containment, it's not that easy, and so I just like to argue a little bit, like try to do some sanity check to see if these objects, they are really doing what they're supposed to be doing. So one thing is, I think I'm gonna skip this proof, but using the Kopsum over games, it's not so hard to see that the cycle of linked sets must have high directory width. So this you can use Kopsum over. And the rough idea is that the robber can kind of always sit on a good cluster, and since it's always well linked, it can use the well linkedness to move to the next cluster. So that's like the rough idea. And then you can see the cycle of linked sets indeed has high tree width, which is what we expect of something that tries to capture the connectivity of the directed grid. Now the other property that you can get is the following. So you might know already that if you have a large cyclic grid, you can actually find also a large fence inside it. So it may not be so obvious at first, but roughly what you can do is you can start here and then you alternate using the columns and the rows to simulate the columns of the fence. So I can use here my first column to do the path going down, and then I just do like a zigzag construction, and then now the rows, they're going to give me the path going up. Right, so by repeating this, we can start getting like alternating columns on the cyclic grid. And so what we expect is that if the path of order linked sets is doing what it's supposed to be doing, then it must also contain a path of well-linked sets. And now another observation here is that if this fence has size k and k, we need from the grid that it has something like size O of k squared and O of k squared. So you just pay like a quadratic function to go from the cyclic grid to the fence. So let's see what happens with the path of order linked sets. So let's say I have my clusters here. I have my sets A and B. So now we want to get a path of all linked sets inside of this. So what can we do? So let's say, just to make things easier, that I'm going to order. So I have this ordering on both sides, and I'm just going to order everything from top to bottom to make the picture cleaner. So what we can do is we can start here, and we're going to take the top k-most elements, so the ones that are smaller in my ordering. This is like the same thing as taking the top left corner of my cyclic grid. And the next thing that I'm going to do is I'm going to look at my B set, and I'm going to delete the top k vertices here. So what doing this means, I'm going to look now on my other side. So I have this linkage connecting these two sets, but I have no guarantee on how this is going to end. So they can be mapped to anything on the right side. So I'm going to get like k vertices on this side that I also going to delete. And from what remains, I'm going to choose the k topmost vertices that survive. So maybe I have to go like in between, but these are going to be my k topmost vertices on this side. So again, we're going to have like some linkage going from B from this side to my green vertices. However, because I delete the top k-most ones here, I know that this set that I'm going to get here is going to be after the top k-most here. So it means now if I take this set and say this is my A0 prime, and I want to arrive here, I'm going to say this in B0 prime, that any subset of B0 prime is going to be below A0 prime. So what you get is that A0 prime is well linked to B0 prime. And so what I can do now is I can kind of like iterate this argument. So I had deleted k vertices here, and I picked the top k-most ones. So I know that my largest index that I have here, that's going to be at most 2k. So I go on this side, and I'm going to delete 2k vertices. So this is going to kill 2k vertices here. So I just again pick the top k-most ones, and I now can repeat. I'm going to end up in some set here that's going to be below what I had before for A1 prime. And so I can just iterate this. And one curious thing is that we get in the end this path of all linked sets, and the function we pay is basically the same that we did for the cyclic grid. So if I have here something like k square many paths, and I have k square many clusters, then I'm going to get a path of all linked sets with k clusters and k paths inside. So in a sense, we're kind of like capturing what like this connectivity property of the cyclic grid, that it contains the fence, and we're actually not really losing anything in the function. So it seems the path of order linked sets is doing what it's supposed to be doing.
Sorry, why does the number of clusters go down?
Clusters. Does it have to go down? I think. Yeah, I think you're right. I think it doesn't have to go down. Like, I think we just need to have.
K clusters, right?
Yes, K should be enough. Yes. 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 You're right.
Thanks.
Okay, so the object seems to be doing what it's supposed to be doing. Oops. I don't like my browser apparently. So I'd like to give you now like a rough overview on how the proof flows. So we're gonna start, of course, with high direct tree width, and it was already known that if you have high direct tree width, you can get a very large wall-linked set. So basically, our proof works with having this very large wall-linked sets. So the next step is to get what is called a web. So what is a web? That's just two linkages. Let's call them P and Q. And the part that you have is that every path in Q intersects every path in P. Okay, so they can kind of like intersect how they like. But you have that every path key in Q intersects every P in P. In addition, make sure that we get like the cycles in the end. We are gonna have that the endpoints here that they are gonna be well linked. So here I would just like to emphasize on a thing that looks a bit like a tiny detail, but it's actually kind of like very critical here, and that's this concept of minimality. So we're not just, so what we mean by minimality is the following. If I take my linkage P, and I look at an edge here E, such that E is in the edge set of P without the edges of Q. So that's an edge that's only in P and not in Q. So I want to say that it's minimal if, so my linkage Q is somewhere here. If I have like no path from A to B, so this is A and this is B. In D without E. So I kind of think that P is minimal, that I cannot delete edges that only in P. And when I say I want a minimal web, I mean I want P to be minimal with respect to Q, while at the same time maintaining this property that Q intersects every path in P. And this is somehow very, very important, because if I drop this minimality condition, then we can get this with a polynomial bound. But with this minimality conditions, we end up having something like a power tower, I think like of height 5 or something like this. So somehow like this minimality makes things very tricky. Like it's kind of like responsible for like a very huge part of the function. And I believe if it were possible to like skip minimality, there might be like a good chance of getting like a polynomial grid theorem. But I think actually getting the minimal web, I really think it's possible to find pseudo polynomial lower bounds. So I think this is like a important step to determine if you want to get like find out what's the correct point for the grid theorem. I think figuring out what happens with this minimal web is quite important.
Do you have some lower bound that arises from there?
No, I did not try to get lower bounds. But okay, yeah, so now we get this minimal web. So the next step is to try to put a little bit more order into this. And so what we do is we want to kind of have like some ordering from left to right. So P is going to become like some horizontal linkage. It is going to go now nicely from left to right. And Q is going to be more like a vertical linkage, so it's still going to intersect things in a more or less arbitrary ways in any order, but we are going to have that the paths in V are going to be ordered from left to right. And we still have the property that the end stays well linked to the beginning. So now we're slowly getting closer to getting something like a grid or a path order linked sets. And so the next step is to construct out of this path of order linked sets. So what you get is, so we're going to get like the path of order linked sets with our clusters going nicely from left to right. and you're gonna get at the end is gonna be wall linked to the beginning. So we're gonna have like to start our proof with this path of order linked sets. So that's why it's also important that from the path of order linked sets we can construct our path of wall linked sets. And so the next thing that we now have to take care of is to get this backlinkage to be disjoint. So if you now get the backlinkage from the last cluster back to the first one being disjoint, then that's the cycle of linked sets. So the next thing in the proof is if we cannot do this, then we get a linkage R here that intersects the clusters like from right to left. So I try to like slowly give more structure this linkage and try to get it disjoint. And in the end, when we finally manage to do it, then we can finally obtain the cycle for linked sets. And this linkage is going to be the one connecting to find it back to the first cluster. Okay, so that's roughly like the overview of the proof. So I'd just like to give you like a table with what we obtain. So we get for many objects now elementary functions. So I'm gonna write this down again. So for the ordered web, so all of these objects, there are things that like more or less they were already present. So the ordered web was called split and segmentation with the proof of Kawarabayashi and Kreutzer, but it's doing more or less the same. And previously, all of these functions were non-elementary. So we improve all of them to be something elementary. So with the order web, we get a parameter of height 5 for our path of our linked sets. We get a parameter of height 7. And we want to go from this to the grid. We pay one more level, so it goes to 8. We can get the disjoint cycles, so that was Young's conjecture. With a parameter of height 8 and a single grid. With a parameter of height 22. It's like a summary of the functions that I obtain, and some of the clear direction for like future work is can even get any sort of polynomial upper bound. That'll be interesting. Like currently there is so another direction is also about lower bounds. So currently the lower bounds, they are not very exciting. So I think the best one probably so far is something like k square or k. It basically comes from the undirected grid theorem. So it'd be interesting to know if you can get like some lower bound which is like higher than the undirected case. Okay, so thank you very much for your attention, and I'll be glad to answer any questions. Sure.
Yes. So if I only want to exclude the acyclic grid, do I really need a lot of these strong connectivity assumptions, or is there maybe a way to get around it to find the acyclic grid?
So the thing is, we don't really have anything like a directory way for DAGs, right? So we kind of need to start with a well-linked set, but we don't really have like a corresponding parameter which kind of captures this well-linked set. And the thing is, if you ask for something that's somewhat similar, like you are well linked from A to B, then you could have just like complete bipartite graph, right?
Yes.
And then you're not gonna get the grid at all. So like being well linked from A to B still doesn't capture having the grid.
I have a kind of philosophical question.
But when you look at the cylindrical grid, the paths, the spokes, they alternate directions, and the cycles do not. Is this would alternating the directions of the cycles change it dramatically? Would it be a completely different structure, or was it considered anywhere?
So it's not going to really capture true width because this grid does not contain the one you mentioned, right? So you're talking about like using this grid like this, and you're talking the one where the cycles
alternate.
do this.
Yes.
So yeah, so this grid definitely does not contain this one, so this is not true, so you will not be able to get, like you cannot guarantee that you get this one with true width.
So it's some different parameter.
You got a different parameter, which is going to be even, it's going to be smaller than true width, is it? Yeah, because it's going to be smaller than this, so you got a parameter that's even smaller than true width. Yeah. So probably even, like, I think if you do this, you might get like a better grid, but your low width case is going to be even worse. Right, you get like even weaker parameters, so maybe you cannot even do disjoint paths anymore, and that's basically what you can do with true width.
Alright.
But if you get rid of the alternation of the path, nothing happens.
Yes?
Is the entire proof constructive?
Yeah, I think so. Like at some point we use a lowish local lemma, but there are constructive versions of it. So yeah, the whole proof is constructive. Okay, further questions?
If there are no further questions, then let's thank the speaker again.